Hello, my name is Luc Moreau. I'm going to present some work developed in collaboration with Dong Nguyen. The work is concerned with PROV-JSON-LD, which is a new serialization of the PROV recommendation in JSON-LD. For the hypo audience, an introduction to provenance is somewhat not necessary. However, for this recording, I will just deliver a quick Provenance 101. The word provenance comes from the French language, where it means the source, the origin of something. In the context of art, it means the history of a work of art, a so-called pedigree. In the early years of 2000, there was an increasing concern that we were not good at tracking the provenance of our data. Where is this document coming from? How was this plot derived? Where is the raw data for this table? The World Wide Web Consortium, the standardization body for the web, decided it was critical to standardize the notion of provenance for the web. A standardization group was created to define the data model for provenance so that it could be interchanged over the web. The working group defined provenance as follows. Provenance is a record which provides a description of the people, organizations, entities, and activities that may have influenced some data, some document, something on the web or elsewhere. If you have the provenance of scientific results, it should be complete enough to be able to reproduce and verify those results. If the provenance of data and documents is made available to the users, then they can decide to place their confidence in such data and documents. In other words, they can potentially trust them. With provenance information, we can learn from the past. And finally, provenance of a decision is providing the foundations to construct explanations pertaining to that decision.Standardization of PROV started about 10 years ago and lasted for 2 years. It resulted in a conceptual data model called PROV-DM and multiple mappings to technologies such as PROV-O, a known ontology for provenance, PROV-N, a textual notation aimed at humans, and PROV-XML, as XML was still then being used. The standardization process offers different levels of specification, of scrutiny, and therefore of interoperability. At the strongest level of interoperability, we find the recommendations PROV-DM, PROV-O, and PROV-N, which underwent a strict regime of review and demonstration of interoperability. They appear in blue. PROV-XML was defined as a node, not going through the same level of reviewing. It appears in yellow. In addition, my co-author Dong led the design and implementation of a serialization of PROV in JSON. It was called PROV-JSON and was published by the World Wide Web Consortium as a W3C member contribution. This means that it didn't go through the level of consensual design and scrutiny of a W3C node or recommendation. It appears in red. Over the last 10 years, Dong and I have been maintaining 2 open-source toolkits to process provenance compatible with the PROV recommendations. PROV Toolbox, a Scala and Java-based toolkit, and PROV-Python, a Python-based toolkit. These toolkits have been used in various provenance-based applications, such as explanation for automated decision, the PROV Store, which is a repository for provenance, and provenance-based predictive modeling. We have learned a lot about the serializations of PROV and their interoperability. In particular, we've learned requirements that are important for a PROV serialization. We list in the paper 4 of them. Increasingly, we have designed web applications that manipulate PROV. This means that a good JSON format is useful to process PROV from a JavaScript client. Second, any serialization needs to look natural to its targeted user community. For instance, a lot of effort was put into making sure that PROV-O led to natural RDF. Third, having semantic interoperability is critical. Thus, a linked data approach where terms can be mapped to concepts defined in lightweight vocabularies is important. And finally, fourth, serializations should be efficiently processable, as applications are generating increasingly larger PROV files and sometimes are even streaming provenance. In the paper, we perform a gap analysis of the existing serialization against those criteria. In summary, none of them is satisfying those criteria. Some are semantic, but not efficient. Some are supporting lightweight web frameworks, but are not semantic. That's why we designed PROV-JSON-LD, a serialization that meets all those four requirements. Let me give you a flavor of PROV-JSON-LD. On this slide, you see an example of a PROV-JSON-LD serialization. First, it's a JSON format. It means that it can naturally be processed by JavaScript and meets the requirement of supporting lightweight web applications. In the highlighted box, we find a JSON dictionary representing a PROV expression. Within there, we have an explicit @type property with value PROV entity, meaning that this dictionary is the serialization of an entity as specified by a PROV. For resources that have an identifier, here, this entity, we can use the property @ID. And then we may have other properties. In particular, non-PROV properties must adopt the qualified name notation involving a prefix and a local name, the prefix denoting a namespace URI. If one needs to refer to a PROV property, we find here an example showing that no prefix is required, and the name is the one defined in the PROV-DM recommendation. At the top level of the PROV-JSON-LD serialization, we find a context element defining mappings between prefixes and namespace URIs. There is also a reference to an online JSON-LD context, which I'm going to talk about in a minute. In order to add semantics to PROV-JSON-LD, we rely on a key technology called JSON-LD, LD standing for linked data. When we did this work, JSON-LD 1.1 was just becoming approved as a proposed recommendation. It was finally approved as a recommendation in July 2020. The original JSON-LD 1.0 was published as a recommendation back in January 2014. A JSON-LD document contains a context dictionary which defines mappings between terms of the JSON structure and URIs. Using such a context, a JSON-LD parser is able to load a JSON document as linked data. It is this JSON-LD context that allows us to add semantics to the PROV-JSON-LD serialization. On the bottom left, you see a usage expression defined as a relation between an activity and an entity. Its structure is rather similar to the way PROV-DM defines this concept, and also very similar to its XML representation. On the right-hand side, we display the qualified pattern for usage in PROV-O. The PROV-O representation is directional, always pointing towards the influencer of a relation. According to the qualified pattern, a usage can also be expressed as a resource, linked to an entity, x:\dataset1 in green, via the PROV entity property. An activity, x:compose in green, is related to such usage by means of a PROV qualified usage property. When no additional property is associated with the usage, then we can use the shortcut, the binary property PROV used. We can see at the top that the property activity in the PROV-JSON-LD representation is mapped to the inverse of the PROV qualified usage. This technique was already used in an earlier version of PROV-JSON-LD we published in 2016. However, alone it is not sufficient to give a natural encoding of PROV in JSON-LD. On the left-hand side, you can see the encoding of a usage and a generation, which both have properties entity and activity. A default mapping of entity to PROV entity and activity to PROV activity is only partially providing their semantics. Indeed, when we look at their respective qualified patterns on the right hand, we see that they are mapped to distinct properties. In a usage, the property activity is mapped to PROV qualified usage, which has subject of type PROV activity and object of type PROV usage. In a generation, the property activity has subject of type generation and object of type PROV activity. We see how a different mapping for entity can also be defined in the default context and in the context of a generation. There is a novel feature in JSON-LD 1.1 which allows a mapping to be contextualized to dictionaries with specific type as per their field at type. It is this feature that allows the PROV-JSON-LD to have a natural encoding which we were not able to achieve back in 2016. If we zoom in this context declaration, we see that whenever we have a dictionary with a type, PROV generation, we define a context using the keyword @context. In the @context element, we define two properties. Entity corresponds to an object property in whole, defined as the reverse of qualified generation. The property time is defined as a data property with object of type XSD dateType and mapped to PROV @time. The full context definition is available at the URI indicated at the bottom of the slide. A schema is useful to check the syntax of a PROV-JSON-LD document. Such schema is defined in the paper making use of JSON schema. You see on the right-hand side an extract from the JSON schema. Here we define a dictionary for an entity. A dictionary is a type object in JSON schema and has two required properties, @type and @id. Optionally, it can have properties PROV-type, PROV-location, and PROV-label. And then, optionally again, other properties with qualified name format. For those of you familiar with PROV-DM, it is a direct encoding of the text in that recommendation. As far as the values are concerned, we also define their types. The full JSON schema is available from the URI displayed at the bottom of the slide. It is worth noting that there exists a property @type and a property PROV-type. @type is used to type the JSON structure, whereas PROV-type is used to capture all the semantic attributes associated with that JSON structure. We implemented PROV-JSON-LD in PROV Toolbox, making use of the Jackson library and using its extensibility hooks to parse and serialize PROV-JSON-LD. It's only a first implementation, but we feel that already we have obtained reasonable performance. For the purpose of comparison, the baseline is to use the native JSON library to read a PROV-JSONLD representation and create a Java object. This is the brown bar in the third position, about 12 microseconds. Of course, the Java object that has been constructed here is totally generic, consisting of strings, numbers, maps, and arrays, as per JSON definition. However, what we need to construct is a Java encoding of PROV, relying on pre-existing classes of PROV toolbox for all PROV expressions such as entity, activity, agent, derivation. To get an idea of the cost of creating such a data structure, we use a deep copy procedure that is available in the PROV toolbox. It results in the orange bar in fourth position, 7 microseconds or so. To read a PROV-JSONLD representation, one would need 12 plus 7 microseconds, with in addition some further time for the management of the namespace declarations to facilitate their search and retrieval. Therefore, the reading of a PROV-JSONLD representation, illustrated by the leftmost bar in blue in the first column, only shows a minor performance overhead. It's worth comparing the PROV-JSONLD parsing cost with that of PROV-N, the third bar from the right. It is significantly more efficient than that of an ANTLR 3 parser. The surprise in this implementation is in the serialization of PROV-JSONLD, which seems to be not as efficient. It is relying on JSON, but it is not as efficient as the Provenance serialization that was encoded natively by writing to a string buffer. We are confident that the performance can be improved. A last point about the implementation is that we perform serialization to and from buffered representation in memory to ave the cost of inputs and outputs. We have not done experiments for very large provenance graphs, as this would require an entirely different setup. But overall, we are satisfied with this type of implementation, as it shows that it is actually usable in practice. There are some lessons we learned about PROV interoperability. The PROV-DM and PROV-O specifications, despite all the best effort of the working group, show differences. For instance, some properties in PROV-DM, such as entity in a generation, are mandatory, when they do not seem to be in a PROV-O. PROV-JSONLD, through its context and schema, was useful to identify those differences, but also forced us to resolve them. It would be beneficial to feed those learnings into the standardization process. In PROV-JSONLD, we have a notion of document, like there is in PROV-XML and PROV-N. It does not exist in PROV-DM nor in PROV-O. Again, it would be good for such a concept to be pervasive in all specifications. PROV introduces subtypes. For instance, a PROV person is a subtype of a PROV agent. No specific JSON construct is introduced for such subtypes. Instead, subtypes are expected to be encoded as semantic typing in the PROV type property of objects. PROV-JSONLD relied heavily on the existence of qualified patterns in order to define context and provide a systematic structure for all PROV expressions. PROV-O, however, does not define qualified pattern for specializations, alternate, and membership. In fact, they were defined as binary relations without identifiers, without ability of subtyping them, and not as a kind of PROV influence. For PROV-JSONLD, we assume such qualified patterns existed and assume specialization, alternate, and membership to be present in an extended namespace, PROVEXT, for PROV extension. The presentation introduced PROV-JSONLD, a PROV serialization that supports lightweight web applications, as it is a JSON format which can be processed by JavaScript clients. It is semantic, as it exploits JSON-LD to map JSON properties to semantic concepts in PROV-O. It provides a natural encoding in JSON, which exploits the contextual mappings of JSON-LD 1.1. It can be implemented efficiently, and the first implementation is available in PROV Toolbox. Besides its pure utilitarian nature of a serialization that we use in some of our applications, this research has highlighted non-issues of interoperability between PROV-DM and PROV-O. We used to have tables providing some mappings between concepts and terms. You can see those tables at the following URIs. However, they were not formal, or rather I should say they were not mechanical. With JSON-LD, we have a systematic and formalized translation from PROV-JSONLD to RDF. With JSON schema, we have a mechanism to formalize many of the syntactic constraints of PROV. This approach could be reused in a future standardization activity to better align PROV-DM and PROV-O. Finally, experience in computer science shows that when a data serialization becomes common, such as XML or JSON, specialized databases get implemented to support those serialization, to persist those serializations, and subsequently query languages get developed. So the question is, what is the query language for PROV-JSON-LD? We leave this as a future work.